I haven't seen you guys in a while, and really I'm not actually seeing you right now. You're seeing me. But welcome back to physics. So I sent you guys those two links to be able to run the PhETs from the University of Colorado that allow you to do the same simulations that we were able to do with actual tools in class, but because we can't actually show up in class for a while, the PhET works really well to be able to give you an idea for what things would have actually looked like. Keep in mind that when you're running the PhETs, they are idealized, and I'll keep harping on that to remind you as we go through it. And there'll be some follow-up questions to what I want you to do with it. So we're going to start off with the pendulums and then look at the mass spring systems within the context of simple harmonic motion. So if you follow the link I sent you, you would see this page for the Pendulum Lab. All you have to do is hit play. Hopefully that part worked out for you. It loads up and we go to intro. And here is your pendulum. What you should have figured out is that you can swing it from any given angle at any length over here with any mass. We'll come back to this idea of gravity and friction towards the end, but this essentially lets you repeat what we did in class with the string and masses hanging from the ring stand. So in class, if you remember, your first task was to come up with a setup where the pendulum, give it a second, oscillates at a 1 second period. So how do we know if it's a 1 second period when this thing's just swinging around on the screen? There's a stopwatch function down here on the bottom left that you turn on. So that in addition to the length of the ruler length that you can use to see how long the pendulum is, which we're able to just set over here, you can also time it as it swings. And so all we have to do is pull it away, let it go in whatever range we want it to swing in, and then time it. Remember, the best way to get any timing pattern so that you know you've got a good result is to count multiple revolutions. So I'm going to wait till it gets to the left and start. I'm going for 10 full revolutions. That's 5 cycles. And I stopped it there, where at 25 centimeters or 0.25 meters, we have about a 1.0 second pendulum clock. Since 10.23 seconds was the time measured for 10 revolutions, average that out is 1.02 seconds per revolution. So as far as your questions, we'll start with number 1. How does changing the length of the pendulum affect the period of its motion? Most of you noticed while you're working in class, and if you didn't do that in class, hopefully the PhET helped you see that the longer the pendulum is, the more time it tends to take to go through one cycle, and the shorter it is, the less time it tends to take. And so if we wanted to say double the time of the pendulum's period, it would be reasonable to think that stretching the length to 0.5 meters or 50 centimeters would get us to the same effect. So we'll use the same mass, we'll pull it to the same 32 degrees we started with previously, let it go, and we'll reset the stopwatch and see if we end up with a 2 second period. That's 5 revolutions. And we ended up with, well, not 20 seconds. Weirdly, if you remember your square roots, the 1.4 is going to be meaningful, but the short answer to how does the length affect the period of the pendulum is that the longer it gets, the longer the period is, although it doesn't appear to be a 1-to-1. As you work your way around exactly what it takes to get a 2 second period, let me just show you what happens when you stretch it all the way to 1 meter. Take it to the same angle. Let it go. And we start. It's taking significantly longer, which is a good thing. We're only now approaching 5 revolutions. We're going to be thorough and let it go all the way to 10. though you've probably seen that we're getting real close to a 2-second period already. Look at that. We have basically doubled the period from what we had at 0.25 meters. Notice that we had to, however, quadruple the length. So again, the longer the length, the longer the period. Although it's not 1-to-1, there appears to be another relationship showing up there. Question number 2. How does changing the mass affect the period? So we already know that this is a 2-second pendulum, so we'll stick with the same length there. Let's see if we change the mass, how that would affect it. Right now we have 1 kilogram of mass. Let's make it a substantially different amount of mass, say 0.5 kilograms, and see what happens to the period. So we'll pull it back to 32 degrees again, just because that's where I randomly started before. Let it go and reset my timer. Here we go. This looks familiar. This looks a lot like it was before. We already hit 5 revolutions. We don't appear to be having much of a substantial difference in the period by taking the mass in half. And at 10 revolutions, we got basically the same period. And so even though the mass was half of what it was, that didn't change the period. And just to double check one more time, because we've got a few extra 20 seconds to spare, we'll put it at 32 degrees again, release it, and restart the timer. And hopefully 10 revolutions later, we'll find ourselves 20 seconds in the future. 5 revolutions again. Sure, the suspense is killing you at this point, but what else are you going to do? Same period. So clearly, the mass doesn't have any effect on the period of motion of the pendulum. Question number 3. How does the starting angle affect the period of motion of the pendulum? Now, as you've been doing this, hopefully, you've been paying attention to the fact that whenever you release it from a starting angle here, say the 32 degrees, on the other side of that protractor setup they've got at the top, there's a matching 32 degree mark. And you can see that it swings back and forth from 32 degrees to 32 degrees. Now, that's not entirely accurate for what you saw with the actual string and mass that we used to make the pendulum before. But that's because this thing's supposed to be ideal and proper simple harmonic motion. If you were to account for friction appropriately, you'll see a slightly different effect, but we'll come back to that at the very end. So, at 32 degrees, we've seen a 2-second period for a 1 meter long pendulum, regardless of the mass. What would happen if we cut that angle down to what's half of 32? 16 degrees. And let it go. We let it run. We'll start our timer again. And if we're 20 seconds in the future, 10 revolutions later, then we know it didn't affect it. If it's some other time, then we've got a problem. Now it's 5 revolutions. 6, 7. I'm sure you're tired of counting to 10 by now. And now you're done. Well, look at that. That's basically the same period. We've got about a 2.0 second period again, even though we cut the angle in half. Let's see what happens if we take it up to 64 degrees and double it. So what a lot of you have said before is that it's going to swing faster, which it clearly is moving pretty fast, but it also has to go over a much longer distance and a much bigger angular displacement. So let's see how that plays out on the period. 1 cycle, 2, 3, 5 cycles, 7 cycles, and 10. Well, interestingly there, that seemed to go a little bit longer. So there appears to be some issue with the angle affecting how long the period is. There's a reason for that. You don't have to go into the entire details of it, but we will pull a derivation later. But for simplicity's sake, if you keep the angle small, say within about 12 degrees, then you're generally going to find that the period stays pretty consistent. We saw even for less than 32 degrees, there wasn't much of a change. And we had to get a lot higher than that before we saw anything substantially different. So let's finish up these 10 cycles. 7. And we're back to about 2-second period. So if the angle is small enough, and again, properly within about 10 degrees, though realistically you don't see a huge difference outside of, until you get outside of about 40 degrees, then you actually have a pretty consistent period regardless of the angle. So we're going to use something called the small angle approximation. All right, let's summarize what we found out about pendulums and add in question 4. First of all, to answer question 4, what's driving or the restoring force behind the motion of the pendulum? Well, the restoring force on the pendulum is gravity. It is pulling the bob back towards equilibrium, and then the bob passes and returns and repeats so on. Now, from the rest of our data, we now know that the length of the pendulum is proportional to its period, but it wasn't directly. Remember, if you double the length, you don't end up with double the period. In fact, you have to quadruple the length to double the period, which means t squared is proportional to the length. The mass of the pendulum does not affect its period, so that has no bearing. There is no bearing between t and m. Furthermore, the angle, provided if it's small enough, does not affect the period of the motion. And so what that leaves us, once we work our way through a derivation later, will be an equation that says that the period of oscillation of a pendulum depends on the square root of the length of the pendulum, and it also turns out to be inversely proportional to the gravitational field strength. So now that you've got the layout for the ideal simple harmonic behavior for a pendulum, go back to the PhET, try a few things, confirm what we claim is supposed to be true about the gravitational field. Remember, that's that button that says you can try different gravitational field strengths. Compare Earth to, say, smaller planets or bodies like Mars and the Moon to larger bodies like Jupiter. Offhand, I can tell you that Jupiter's gravitational field is about 25 meters per second squared. The Moon's is only about 1.6 meters per second squared, and Mars's is about 3.5 meters per second squared. So try those, and also try adding friction and see if the motion of the pendulum looks even more realistic to what you experienced in class. See if it actually is bobbing back and forth the way you would expect an actual string with a mass tied to the end of it. So give those a shot, and I'll follow up with more work for the pendulums. On to the mass spring system. Right now, for masses and springs, this would be the page that the link I sent you takes you to. We start the PhET, it revs up, we go to the intro page, and what you find is that you've got a collection of a handful of masses, and we want to know how these masses and spring systems behave in any kind of oscillatory pattern. In general, what you're going to find whenever you put a mass on a spring is that it's going to bounce up and down, and it's going to follow similar to what you saw with pendulums. If there's no friction, an infinite pattern of it bouncing up and down for quite a long time. This spring constant has to do with essentially how stretchy or tight the spring is, and it's going to have something. It's going to have an effect on where the equilibrium position of the spring is. So you notice this is where the 100 gram puts the spring. A 250 gram puts the same spring at a much lower equilibrium position, and then if you put a 50 gram mass at the spring, you have a much higher equilibrium position. Similar to what we saw with the pendulum, we can pull out a timer as well as a ruler to see the stretches, but it's also helpful to click this thing that says equilibrium position, which gives you a mark as to where that mass will end up stretching the spring, and you can see the natural length point showing up at the bottom where the spring would be if it was unstretched. So if we change the spring constant and make it a bigger spring constant, notice that the equilibrium position gets closer to the natural length. If we make it a smaller spring constant, then the equilibrium position gets further away. This is governed by something called Hooke's law that describes the behavior of something called an elastic force, which is how springs, rubber bands, and other kind of stretchy things that return to their original shape, remember that idea of elasticity from collisions, how much that force pulls. And so this spring constant ends up describing essentially, again, how stretchy or elastic a particular body is. And so the bigger the spring constant, the more force is required to stretch it. And so for this small spring constant, you'll see that a 100-gram mass stretches it considerably further than a 50-gram mass, about twice as far. But if you made a much larger spring constant, then you see a stretch that's not nearly as far. Finally, for the 250 grams, see, it stretches it that much further versus the small spring constant lets the 250 gram end up right down here. We're going to pick a spring constant that's roughly in the middle and proceed from there. So, what we want to figure out are the following questions. So, first question, how does changing the mass affect the period of motion of the spring? So first of all, we already know that by putting a given mass on the spring, we're going to have lower equilibrium points depending on how big the mass is, because the bigger the force, the more the spring stretches. Now, in order to get the spring to actually start oscillating, we have to stretch it away from where it was started. And so to keep that consistent, I'm going to put a movable line that will be some given distance below where the equilibrium position is. So if we have the equilibrium position here, we'll always stretch the mass to, let's say, line up 10 centimeters away, just to keep things even. So I pull the mass down to 10 centimeters, let it go, and it bobs like this. And so if we start a timer when it gets to the bottom red line, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We apparently have a 0.5 second period for this mass spring system. But if we were to double the mass to 100 grams, notice that first of all, we again have a lower equilibrium position. And so to get a similar stretch of the spring, we'll have to pull the mass down even further, which would be to here, and then let it go. That's already oscillating slower. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, now we have a 0.75 second period. Well, that is considerably, well, not considerably, but that is definitely slower and a longer period than the 50-gram mass had. So doubling it apparently makes for a longer period, but not again in 1-to-1. So that's interesting, similar to the way the pendulum was. There was a way to add an extra mass. So we're going to swap the 100-gram mass out for a 250-gram mass. We're going to equilibrium for a second. So its equilibrium position is even lower. So we're going to have to stretch it 10 centimeters below where that point is, just to keep things regular. So if we pull the mass down to here, let it go, you can see that going even slower. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that is all the way over, already over a 1 second period, which means that clearly the bigger the mass, the longer the period. So what about the spring constant? Well, we started right in the middle. We'll keep it with the 250-gram mass and see how we can affect that. So let's go with a very small spring constant all the way down to here, which means we're going to require a stretch all the way down to this point. So that's another 10 centimeters, and we'll see how that affects the period of the motion of the mass spring system. So with a very small spring constant, let's see how close we get to 1.1, 1.2 second period. Let's pull it down to, I have to raise it up actually. This screen is not long enough for that mass spring system, so I'm going to raise it up. So this time, to get the same stretch, pull it up to 10 centimeters, because I can't pull it down far enough for it to work out. Let it go, and we start our timer. 1, 2, 3, 4, 5, 6, 7, and this is clearly going longer than the previous one did. And that's 10 revolutions, so we went up from 1.2 to 1.8 seconds by getting a much smaller spring constant. So it stands to reason that if we made the spring constant larger, go to the biggest one, that we'd expect to see a much bigger, a much smaller period. So they seem to be inversely related. Pull it down another 10 centimeters. Notice the spring's a lot bigger now, which is part of a reflection of the PhET simulation to show that generally stronger springs tend to be bigger coils. Let it go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we've got a 0.9 second period for the same mass but with a much larger spring constant, which suggests again an inverse relationship between the spring constant and the period of the oscillation of the pendulum. The last question, how does changing the stretch affect the period? So we'll keep the same largest spring constant we've been using for the last trial, the 250 gram mass we were using, but now instead of stretching at 10 centimeters, let's double that to 20 centimeters. Just make that clear. I'll move the ruler down. We stretch it down to here, release it, and start timing. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Well, look at that. That's still about 0.9 second period. Let's see what happens if we were to stretch it even further. So we'll go ahead and quadruple the stretch down to 40 centimeters from our original 10. Pull the mass all the way down here. Let it go. Well, it's clearly going faster, but it's also got a bigger distance. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Back to 0.9. So it looks that like stretching the spring further or less doesn't actually affect the motion. In fact, let's see what happens if instead of even stretching it, we bring it up only 5 centimeters above where its equilibrium position is. Let it go. It's going slow, but has the period changed? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It hasn't. So clearly the stretch actually has no bearing on how long the period of oscillation is. The mass and spring will oscillate at higher speeds, but they have to cover higher distances for big stretches, and so the period ends up being the same. All right, now let's summarize what we know about mass spring systems and answer question 4. So as far as question 4 goes, what's the restoring force for a mass spring system? Well, that's going to be the elastic force. We label that F sub S, and something called Hooke's law summarize how it relates to the stretch of the spring by this equation. The K is the expression for the spring constant. The delta X is how far the force stretches the spring. And that negative shows up in there because the elastic force is always pulling back at the end of the spring because the spring's trying to pull the mass back up when the mass stretches down towards its equilibrium point. Or you could also think if you compress the spring, at the end of the spring is going to push back down to again try to return the spring to its equilibrium point. The important term in here is going to be that K, that spring constant. Now, from our data, we now know that the mass is proportional to the period of the system's oscillation, but again, not directly. We saw that doubling from 50 grams to 100 grams did not actually double the period. It only brought it up by, turns out again, a square root term. So, turns out that the square of the period is what's proportional to the mass. And then we noticed that the spring constant is inversely proportional to the square of the period of the system's oscillation. How do we know it's inversely proportional to the square? Well, we'd have to do a few more careful measurements to know exactly what the spring constants were that we were moving along that dial, but it turns out that t squared is inversely proportional to 1 over k. Finally, the initial stretch had no bearing on it, so however much delta x was, was related to force and decay, but it turns out to not show up in the period. So when we put all this together, the period for a mass spring system's oscillation depends on the square root of m over k. So you've got the mass spring system, pendulum, and pendulum period equations to work with. In another day or two, I'll follow up with some other work for you to be able to actually run calculations on it, and then we'll have a full derivation for where that equation came from, starting with the idea of what the actual restoring force is. The restoring force for the pendulum was gravity pulling down on the end of the bomb, although it works better to treat it as a torque, and the restoring force for the mass spring system was the elastic force described by Hooke's law. But again, we'll save all of that for another day. Thanks for showing up for this, and I'll check in with you guys sometime soon. We got nowhere else to go, so see you later.